All right, so we're going to talk today about quadratic models. So far we've seen linear models, we've seen exponential models, which is talking about growth or decay. And today we're going to talk about quadratic, and tomorrow as well. So first off, which model is which? Which when do we use and when's the situation? So this is a brief summary of things. So when do we use a linear? That's when we have a constant amount of change. A constant amount of change. And by the way, the delta, the triangle there, that simply means change in math. And of course, generally, we're adding or subtracting. We're adding 2, adding 2, adding 2. Subtracting 10, subtracting 10, subtracting 10. Something like that. All right. And of course, our basic shape for a linear model is going to be a line. Now, the line can go upwards or downwards depending on if you're adding or subtracting.
What does that say in the first one?
Next, the exponential. This one is not a constant amount, but it's a constant percent of change. So, constant percent of change. Good, and this generally applies if you are multiplying or dividing each term. Times 2, times 2, times 2. Or a 5% growth. Or half-life of 2 years. Something like that. Things are dropping as in decay or growing as in population. The exponential basic function, there are two ways to do it. A growth function just goes like that. Generally, or the other one is dropping down like that. So that would be the decay function, second. Growth function first. Now, a quadratic might be easier for us to look at the situation first. If I were to toss a ball up in the air to my friend over there, then it would look like this, the path of the ball. But we could also have something sagging like so. And what's the major difference between the graphs so far? Notice this one has constant growth. So does this one, constant growth or constant decay? But this one has a massive change. It's growing but then drops down. Or it's dropping down and then suddenly it picks back up. So this one talks about when there's a max or a min. When there's a huge change. And oftentimes, this is huge in physics. This describes a lot of physical model situations. Now, for a quadratic, we don't actually always have to focus on the vertex. It can just look right here. We can just be talking about this right here and then stopping there. So it could be discrete. In other words, we're just talking about a particular part of it. Or we could be talking about this right here, where here it just grows exponentially. So we're not talking about the backwards growth. We're talking about a forward growth, exponential growth. All right. So in our final moments of class, let's take a gander at a few of these by review. So Algebra 2 days, a year ago almost, 6-8 months ago. A quadratic function is an equation that can be put in the form, and it looks like we're going to do standard form. So f of x is equal to ax squared plus bx plus c. All right, so let's see where we left off here. A quadratic function is an equation that can be put in this form. We call this standard form, but for our sake, this is just the one thing we're going to use. Next, the basic shape is called a parabola. And a parabola basically looks like this. Notice it's not a perfect U, because the U tends to go vertical, up and down. This doesn't. It never goes vertical. There are no asymptotes. I always say that word wrong. On here. It just keeps going out forever. It just goes up faster than it goes out. You may recall back in the day that when A is greater than 0, something happens. And if A is less than 0, something happens. And more specifically, so if A is greater than 0, then this thing opens upward. It opens up, so it's going to have this basic shape like so. A way to think about this is that if A is greater than 0, A is positive. Therefore, A is happy, and we got a smiley face. If A is positive, happy face. Next, if A is less than 0, you can think about that as negative numbers. So therefore, we're going to open downward and look something like that. And of course, you can consider that to be like a sad face. All right, the and part is that if it does open upward, it means this will have a minimum point. So we can just call it simply a minimum. That means the function drops down, gets to the lowest it can go, and then continues to go up. Alternatively, if our graph does this, where A is negative, then this has a maximum. And the maximum is the highest it goes. Like when you throw a ball, it gets to its maximum height and then comes back down. So this would be A is 0. Salud. The domain generally is all real numbers, because that means the x values are all real numbers. Now, I'm not saying always. I'm just saying mathematically it's all real numbers. In real life, you might not be able to go back in time, or you might not be able to throw backwards, something like that. So, and the range is above or below, or let's actually switch that around. I'll say below or above the max or the min. So it's below the max or above the min, depending on which direction of the graph. Next, something else you may or may not have remembered. C is always the y-intercept. No matter what C is, that's where it crosses, the graph crosses the y-axis. We often will say that the x-intercepts, we also call them the solutions. Sometimes they're called roots, etc. And they only exist when b squared minus 4ac is greater than 0. Good. So this here is called the determinant. And notice that if this is greater than 0, it's a positive number. And you can take square roots of positive numbers. If it were a negative, then it would go into the complex numbers or imaginary numbers there. So that's why we have to keep it greater than 0. Officially, though, you could probably be greater than or equal to, because even if you have 0, you just have one solution.
5% battery.
It's found by using the quadratic formula. And the last thing is the vertex can be found by using this right here. Notice that this is the quadratic formula, just without the determinant. Discriminant. X equals negative b, blah, blah, all over 2a. So let's finish up here and just identify some things right here. This is called the minimum. It's also the vertex, or the vertex is a minimum. In this case, a is greater than 0 because it's going up. Right here, this is my y-intercept. Therefore, it is also my c. Over on this side here, let me finish up. This one is these are my x-intercepts, also known as my roots. So they're called your roots. They're called your x-intercepts, also called your solutions. Oftentimes it'll say, like, when will the ball hit the ground? And that's usually what we're trying to find. We're trying to find when the ball is at 0. Over here, notice that this is the x-axis right here. And my curve never touches the x-axis. So in this case, b squared minus 4ac is less than 0. So that means we won't ever get solutions. So sometimes it'll say no real solution. Or if we tried to solve it, we'd have to go into complex numbers. So there are no x-intercepts in this case. There is a y-intercept right there, and that's your c. Clearly, because of the downward trend, we know that a has to be less than 0. So a is probably, or is a negative. We're going to consider this function right here that's called f with the equation f of x equals negative 3x squared minus 4x plus 7. So we're going to find the x and the y-intercepts. What's nice is the y-intercept is super, super, super easy to find. There it is right there. Y-intercept is simply 7. Now, you can write it as just simply 7 if you say y-intercept. Otherwise, it's a point, 0, 7. Now, how do we find the x-intercept? To find the x-intercept, what we're saying is, when does my function get to 0? So what I have to do here is set this one up, negative 3x squared minus 4x plus 7. And what we have to do, and we'll do it by hand here, and I'll also show you how to do it technologically, is we have to solve this using the quadratic formula. So x equals negative b, and here's my b, plus or minus radical b squared minus 4 times a times c, and I'm going to draw my radical to go all the way across, all over 2 times a. And keep going here. I'll simplify. This says 4 plus or minus 16 plus 84, keep the radical around it, all over negative 6. 4 plus or minus the square root of 100, all over negative 6. Yeah, we'll get to it. So 4 plus or minus 10 over negative 6. So 4 plus 10 is 14, and 4 minus 10 is negative 6. So here are my two solutions. So here are my two x-intercepts. In other words, the x, it'll cross the x-axis at negative 2 1/3 or at positive 1. And depending on context, one of these might not make sense in the real world. So let's now find the vertex here. And if you recall how to find the x-coordinate of the vertex, what we have to do is x equals negative b, all over 2a. So it's everything but the discriminant. It's just the negative b over 2a. So all we have to do is plug in the values. So I say negative, and my b here is negative 4. So notice I have a negative in the front, and I have way too many negatives there, so let me clean that up. And a negative on the inside. So I have a negative in the front and a negative right there. And another negative right here, the negative 3 inside. So now I have a triple negative. So if I go ahead and drop out 2 of those, now see what we get. The 4 and the 2 can reduce. So I get negative 2/3. Now, in order for us to calculate this, we have to take the negative 2/3 and we have to plug it back in to the original problem. So this here is where things get dicey because we're putting in a fraction, we're squaring it, etc. So I'm going to plug it in and just jump straight to my calculator. So this is what it looks like. The y value is going to be this. Negative 3 times negative 2/3 squared minus 4 times negative 2/3, all plus 7. And when I plug all this into my calculator, I get 8.33 repeating forever, or 8 1/3. So that means my vertex is negative 2/3 and positive 8 1/3. One of the most important places that quadratic models show up are in physics. So to calculate the height of an object, so follow along slowly because there's lots of letters. But don't panic because every single letter has a meaning and all we have to do is start substituting / solving. So h is the height of the object. So an object is thrown and we want to know how high it is after a certain number of generally seconds. Okay, so t over here, this t and this t are seconds. All right, so we can find, the height can be found using this formula. H equals negative 1/2 g times t squared plus v naught, or v sub 0, t plus h naught. Where g is one of two things. If you're in the metric, it's 9.8 meters per second squared. And the other one is 32 feet per second squared. And that's a 3 there. V naught, or V sub 0, is per second. Is your initial velocity. That is, how hard are you tossing the ball, how hard you throw in the airplane, whatever the case is. However hard you throw it, that's going to be a speed, 10 miles an hour or 6 meters per second, something like that. Question. And h naught, or h sub 0, is also known as the initial height. Where is the object, not necessarily where are you standing, but where's your hand? About how high is your hand when being tossed? All right, so a ball is thrown upward, so we know that we have a positive initial velocity. From a height of 15 meters with an initial velocity of 20 meters per second. Notice it has meters here, so I'm going to be consistent, so I'm going to use the 9.8 there. So my function looks like this. My height is, and I'm going to put in the negative 1/2 to begin with. Now I'm going to substitute in the 9.8 for g. That's the acceleration of gravity. And t is unknown, so I put my t squared there. Plus my initial velocity is 20, so I put a 20 there. Again, t is unknown, how many seconds. And my initial height is 15 meters. So there is my function. I can simplify a little bit. Notice I can clean that up if I needed to. But for now, we'll leave it like this. So next, how high is the ball after 3 seconds? So this is a straight evaluation question. All you have to do is evaluate the function at 3 seconds. So h is going to be negative 1/2 times 9.8 meters. And I'm going to substitute in here 3. And 3 there. Plus 15. Now, of course, the fastest way to do this is if we were to put this function into our y1 on our calculator, and then all you have to do is say y1 evaluated at 3. So I'm going to go ahead and do that. After I plug this into my handy-dandy TI-84, I get approximately 30.9 meters high. 30.9 meters high. And the next question is, when does the ball hit the ground? So that's a question about x. So one way to solve it is by hand, using x equals negative b plus or minus radical b squared minus 4ac all over 2a. Or we're going to graph, essentially we're going to graph the function, which is going to look something like this. And we're just going to find out what the x-intercept is right there. So after I calculate this, x is approximately 4.72 seconds. So I throw the ball from 15 feet. 15 meters. Thank you. It goes up, it hits a max of some sort, and then it comes down, and it takes almost 5 seconds to hit the ground. One other question that might be asked of us is, what is the highest that it reaches? That's a vertex question. So all we need to do is plug that into our calculator, do left bound, right bound, and a guess, and we can find out the height. I'm going to go ahead and do that now, just so that we have that process as well. So after I plug all that in and find the max, the maximum here is approximately 35.4.